Hi everyone, we are on the last part of section 2.3 now, and I think I promise anyway, that this video will be shorter than the last one. So in this video, we're specifically going to go over the absolute value function and how to take the limits when we have an absolute value function. The reason that we have to go through this separately is because the absolute value doesn't have a specific limit law that works for it. So we can't just take a limit and run it through an absolute value. What we're going to do first is discuss what we do when we have absolute values and why we have to go through that process. Okay, so when we're doing calculations with absolute value functions, what we have to do is think about it in two different parts. If we don't think about this in two different parts, then it can change the result of what we get. So we have to go through this process because the absolute value functions behave differently on each side of the vertex, right? Like I said before, you can't just run the limit through it, so it's really important that we go through this process. All right, so let's start with just the simplest form of an absolute value equation, and that's just the absolute value of x. All right, let's think about this both visually and computationally from both sides. If we're thinking about it from both sides of the vertex, we can represent this with a piecewise defined function. So a function that's defined in two different parts. Right, looking at the left-hand side, and I drew this out visually down here, looking at the left-hand side of this function, you would actually have the line y equals negative x. So looking at the left-hand side of this, our y-intercept is 0, right? Y-intercept is 0, okay? And now looking at the slope of this line is, of course, negative 1 over 1. So we go down 1 over 1, down 1 over 1. So the slope of that line is negative 1, which means that our equation for that would be f of x equals negative x plus 0. All right, the next thing we need to consider is where the vertex is. Right? So in this example, the vertex is at 0. So in a piecewise defined function, you always have to have a split point because it's defined in different pieces. So I'll say that we have our function equaling to negative x if x is less than 0. And if I want to, I can write equal to 0. I can put that in either part of this piecewise defined function, and that's because they're the same value there, the same y value, which is 0 there, so that part won't matter. Okay, looking on the right-hand side of this, I see that my y-intercept is still 0, so really I have plus 0, but I have a positive 1 for a slope here. So on the right-hand side of this, this is really the function f of x equals a positive x plus 0. So this is the same thing as just a negative x if I'm looking at the left-hand side, and a positive x if I'm looking at the right. We have to finish our piecewise definition. So this is if x is greater than or equal to 0. So that really means on the right, and this really means on the left. Right, in the equal to bar, it doesn't matter where you put that. Okay, so visually, usually when students think this, they're like, oh, well, like it approaches the same value. They have both approach y equals 0, so why do I have to make that adjustment? We are going to see that soon, but first, let me show you how to carry through this specific example computationally. So we see what it looks like visually. Let's see what it looks like calculation-wise. So if you're going through calculations with limit laws and limit notation, what you have to do is split into two parts. Split into two parts from where the vertex is. Okay, so if we look from the left, we have the limit as x goes to 0 from the left, 0, the x value of 0 is where your vertex is, that's why I have the 0 there, of x, so of the absolute value of x, sorry, equals, all right, now I have to use that piecewise defined function, so I know that when I'm on the left-hand side, my absolute value function is the same as y equals negative x. So now I'm going to substitute that negative x in there. All right, at this point, I've done some good work because now I can use the limit laws. So by the limit laws, when I run the 0 through here, this is just equal to 0. Okay, we need to explore this from the right as well. So I'll take the limit as x goes to 0 from the right of the absolute value of x. I should see that from up here, this is really a positive x, so this is equal to the limit as x goes to 0 And I actually don't even have to write the little plus or the little minus here. I can, it's not wrong, but I don't have to, and that's just because I made that substitution in there. I put the negative x and I'm putting the positive x, so it's not necessary, but you can write it if you want. Okay, so I'll put the x here. Now I can in fact run my limit through, and that would get me 0. All right, so in this instance, if you were to make the argument, oh, well, they're approaching the same thing, why don't I just use that? You're absolutely right. These two approach the same value from the left and from the right, so you could simply say the limit as x goes to 0 in general, so from both sides, is equal to, so of the absolute value of x is equal to 0, and that's because your limits on each side match, just like we saw in section 2.2, the same concept. Okay, so the thing is, not everything is going to be as easy to draw out or to look at as this. So this one, a lot of us probably see, oh, absolute value of x, and have an idea that it's, you know, the V-shaped function with the vertex at 0. We probably remember that from pre-calc. But if you have something more complex, you're not necessarily going to remember that, and you're not guaranteed that you have the limit, you know, equivalent. So, for example, let's calculate the limit as x goes to 0 of the absolute value of x over x. I should notice immediately that I have an absolute value, so I must split this into two parts. So absolute value, I must split into two parts. Okay, so I need to look from the left. All right, and from the left, the notation I'll use is the limit as x goes to 0 from the left of the absolute value of x over x. All right, now I know that when I'm on the left-hand side, this absolute value up here is really equivalent to negative x. So I have the limit as x goes to 0. You can write from the left if you want to, but you don't need to because I'm making an adjustment now, of negative x over x. All right, so from here, negative x divided by x is a negative 1. So I have the limit as x goes to 0 of negative 1, which is going to be negative 1. All right, let's see what happens on the right-hand side of this. So from the right, we have the limit as x goes to 0 from the right of the absolute value of x over x, which is equivalent to the limit as x goes to 0 of x over x. So remember, when we split this, if you're coming from the right, it's really equal to x. Right? This divides out to 1, so we have the limit as x goes to 0 of 1, which will give us 1. All right, so on this we should see, those do not agree. They're not the same, which means we would conclude that the limit does not exist. So I know the limit does not exist, and that's because it's different from the left and right. Okay, so on that one, the limit doesn't exist, and I hope now you can see why it's important to not just run the 0 through the absolute value. In this case, you would have gotten something undefined anyway, but we can see since these behave differently from each side, we have to take both sides into consideration. All right, as promised, keeping this one shorter than the last one. So last example in the notes is going to highlight a crucial mistake that people make fairly often. All right, so looking at this, I see I have an absolute value that clues me in right away that I have to look at this from both sides. Sometimes people don't recognize that this is a negative 6 here, so this is going to be a little bit different than our first example. So in the first example, we just had the absolute value of x. There was nothing else in there. In our second one, we just used the simple absolute value of x, so we didn't have to do much. Now we have the absolute value of x plus 6, so I have to think about this in steps. So if I have x plus 6, I'm going to define this piecewise again. I'm going to draw out a picture so you can see what it looks like. We'll go through the same thought process that we did in the first example. All right, so I just sketched out a picture. Hopefully remember from pre-calc, if you don't, that's okay, that when you have an absolute value function, if there's a value inside of the absolute value, then it means the vertex shifts over to the left by that many units if it's positive. So this is really just the absolute value function shifted to the left by 6 units, which means it looks like this. All right, so now if we're thinking about what this looks like coming from the left, so I'll write as x is less than 0 to mean on the left-hand side, then I know that I certainly have a slope of -1. I can see the slope goes down 1 over 1. So the slope is -1 or -x. All right, if I extended this line all the way down, I would find that the y-intercept is -6. Right, so really what's happening here algebraically is, since it's on the left, we have a negative out in front of the whole thing, and that gives us a -x minus 6. Visually what's happening is if we plot out this line on the left-hand side all the way down, we'd get the slope of -1, so -x, and the y-intercept of -6. So that's where that comes from. Okay, looking at this from the right-hand side, we just keep the positive part. So here we can see that our slope is a +1, so we get x, and it intersects at the y-intercept of 6, so we get +6. So this is where x is positive or greater than or equal to 0. Again, it doesn't really matter where you put that equal to line right here. Okay, so now we know what this looks like from the left and from the right. What we have to do is make that split algebraically. So going through that, let's explore this from the left, right? What we have for that is the limit as x goes to -6 from the left of 2x plus 12 over -x plus 6. It's generally easier to just leave the negative on the outside. You'll see why in a moment here. All right, so looking at this, I see that I can simplify. So this is equal to the limit as x goes to 6 from the left. Again, it doesn't matter if you write that negative or not. But anyway, of 2 times x plus 6 over negative times x plus 6. Here the x plus 6's divide out, and that leaves us with the limit as x goes to 6, from the left if you wish, of -2, which is of course just -2 because the limit of any constant is itself. All right, now we have to go from the right. So coming from the right, we have the limit as x goes to -6 from the right of 2x plus 6 over x plus 6. Again, the 2 factors out, so we have the limit as x goes to -6 from the right of, whoops. All right, of 2 times, this should be a 12 right here. Okay, 2 times x plus 6 over that x plus 6. Dang it. All right, so from here, our x plus 6's divide out to 1, and we're left with the limit as x goes to 6 from the right, or you could just say as x goes to 6, of 2 over 1, which is just 2. All right, so here, reaching our final conclusion, we see the limit from the left is different than the limit from the right. Therefore, we would conclude that the limit does not exist. The limit does not exist. There we go. All right, so that takes care of this part.